Screen share. Ready? And give me a second here. There we go. Okay. Welcome back, everybody. This is the 2022 Virtual Residency Workshop. It is Monday, June 27th. I'm Henry Neeman. This is our second session. This is the effective communication session. And let's dive right in. I hope everybody's ready to go. So here we go. Quick outline. We're going to talk about how to talk to researchers and about research terminology. I'm going to give a comparison between enterprise IT and research computing. We're going to talk about the mindset gap, and I'll explain what I mean by that when we get there. We'll talk about different types of researchers, what to say to a researcher, how to find the researchers, and how to find their projects. Now, I think I have the right amount of content, but you never really know. So if I run out of time before I run out of content, I'll just stop. And if I run out of content before I run out of time, that'll just be question time. Okay, so let's talk about how to talk to researchers. So I want to start with a quiz or a poll. I'm not going to do it with a polling mechanism, so we'll just do it in the chat. Or you can do it by show of hands with the put your hand up button. How many of you believe that oxygen is a metal? You can put it in the chat, yes or no, or you can put your hand up on a little show of hands thing. But I just want to know how many of you believe that oxygen is a metal? I have one yes and two no. In the chat, I have a yes and a no, a whole bunch of no's. Oh my goodness. Lots of no's in the chat. And I have one yes and 8 no's in the buttons, in the little icons. Good astronomers say yes. In stars, yes. Everybody else is saying no. That's not a coincidence, and we'll get there in a minute. It depends. Thank you, Hussein. That is the best answer. Okay, so it looks like the consensus is oxygen is not a metal. Well, let's dig into that and find out what we really believe. Okay, so what is oxygen? Well, I looked it up on Wikipedia. It's atomic number 8. It's a chalcogen, whatever that is. I guess that's a chemistry term. Of course, you need it to be alive, right? We're constantly breathing it in. You also need it to have fire burn. You need it for rust. You need it for water, right? So H2O, it's not a coincidence. Is this an example of being 5 seconds ahead of us? Yes, but it took me 20 years to get 5 seconds ahead of you, Annalie. What's oxygen in astronomy? Well, to understand the answer to that question, we have to understand some other things in astronomy. And in particular, we have to understand what the universe is made of. Now, I'm carefully excluding dark matter because we don't know what that is. So I'm only talking about visible matter. But visible matter, if you're going to bake a universe like you'd bake a cake, the #1 ingredient that you need to bake a universe is hydrogen. Now that's atomic number 1, and it is 3/4 of all baryonic mass. I do not pretend to understand what the word baryonic means in this context. I am a computer scientist, not a physicist. Most stars are made of hydrogen, right? Okay, so now you've got hydrogen. You have a big pile of hydrogen to make your universe. What's the next thing you need? The next thing you need is helium, which is, not coincidentally, atomic number 2. It's an inert gas, a noble gas, and it is 24% of all of the elemental mass. Now, I don't know what the difference between elemental mass and baryonic mass is. I don't know what elemental mass means. Again, computer scientist, not physicist. I don't know any of this stuff. But it can't be a coincidence that 75 plus 24 is 99, right? So almost all of the visible matter in the universe is hydrogen and helium, okay? Everything else squeezes down into that 1%. So that includes oxygen. And it also includes everything else. What's a planet made of, right? Because we think of planets as important, we live on one and so on. What are planets made of? Well, planets basically are made of metals in the traditional sense, the sense of hard, shiny things. Now, of course, mercury is a metal that is liquid at room temperature, but most metals are solid and hard at room temperature, right? So the core of a typical planet, well, Earth's, for example, is almost 90% iron and 95% iron and nickel, right? And 5% everything else. The mantle is stuff like sand, right? Silicon, but it's, to first order, a planet is made of metals, right? And in fact, it turns out that the reason barns are painted red is because dying stars throw off iron, right? There's a lovely link here to, I reread the article a couple of days ago just to make sure that it was still there. It's pretty interesting. So what does it mean, metals, right? Well, if you're a chemist, you have a very specific definition of what a metal is, right? And in this diagram, all the yellow bits are metals. All the orange bits are semi-metals, whatever the heck that means. And all the green bits are not metals, right? So you can see hydrogen, helium, and oxygen, those are non-metals. But most elements are either metals or semi-metals. So far, so good? Now, again, if you're a normal person, you think of metals as shiny, hard things. If you're an astronomer, the word metals to you does not mean shiny, hard things. The word metals to you does not mean the yellow bits in this diagram. The word metals to you means things that are neither hydrogen nor helium. Metals to an astronomer, and especially a cosmologist. A cosmologist is an astronomer who studies the entire universe over its entire lifetime, right? So uncountable megaparsecs over, what, 14-ish billion years or whatever, right? My PhD advisor is a cosmologist. And so I would sit in these meetings. They would have he'd have like a weekly meeting. We'd get together and people would talk about their research. And I'd sit in these meetings and people would use the word metals. And for 3 years, I assumed that they meant shiny, hard things. And it wasn't until I'd gone to, I don't know, 150 of these meetings or something, I don't know, that it finally dawned on me that when they said the word metals, they didn't mean shiny, hard things. They meant not hydrogen, not helium. That was a huge revelation for me. And it changed my perception of all these discussions that we had been having for 3 years. Okay, so that's one thought experiment. Now, let's talk about the word projection. Let's say that you lock in a room a mathematician, a psychologist, and a movie producer, and you say, talk about projection. What's going to happen, right? What does projection mean to a mathematician? Projection is taking a shape in a thing in a higher dimensional space and mapping it down to a thing in a lower dimensional space, right? The classic version of this is taking a cube and projecting its shadow onto a piece of paper where it looks like 2 squares and some diagonal lines between the corners of the 2 squares, right? That's a projection. It's not a 3D object. It's essentially the shadow. It's the reduction of the 3D object to a 2D simplification. What's projection mean to a psychologist? It means assuming that other people have the same emotional reaction or reasoning or whatever that you do about the same thing, right? You often hear people using this when they're making ad hominem attacks in an argument. On the other hand, to a movie producer, projection means shining light through a transparent but colorful or maybe black and white medium to put an image on a screen far away, right? Those are 3 different meanings of the word projection. Now, admittedly, the math meaning and the movie meaning are related, but not in a way that's obvious to the mathematician and the movie producer, especially the movie producer, right? So here's a key skill. And by the way, we've been talking about this for the better part of a year in the sifted discussions, and I've come to an understanding about myself. I can do the following thing, but I can't tell you how I do it. You develop the skill through experience of being able to detect when people are talking past each other, including when they're talking past you, when they're using words in different ways, right? Using the same word to mean different things or different words to mean the same thing. And when you learn how to notice that, addressing it is straightforward. You just point it out and you say what the one person is using the word to mean and what the other person is using the word to mean. And people, once they understand that they're talking past each other and how to fix it, they can fix it. What they can't do, what's the hard skill, and what I don't know how to articulate how I do, is to detect that people are talking past each other. I know I can do it because I've done it any number of times. I flatter myself that I'm good at it. I can't tell you how I do it. The minute I figure out how to explain how I do it, I will write a lesson about that. So far, I don't know what it is. If you want to see a classic example of this, I've put a link to, on YouTube, there's the classic Who's on First routine from Abbott and Costello. That's a beautiful example of people talking past each other. What's a fluid? Well, normally in colloquial English, we think of the word fluid as meaning the same thing as liquid, right? And then, of course, there's your mom and your doctor who say fluids are things you drink plenty of when you're sick, right? Have some orange juice, have some tea, whatever it might be, because you've caught a cold, right? That is not what physical scientists and engineers use the word fluid to mean. They use the word fluid to mean not solid. And in particular, in computational fluid dynamics, which many of us facilitate, the most popular fluid to work on is air, right? The Earth's atmosphere, which is obviously a gas or a mix of gases, right? So dictionary.com has it as a substance as a liquid or gas that is capable of flowing and that changes its shape at a steady rate when acted upon by a force, right? So liquids are a subset of fluids under this definition. Liquids in particular are incompressible fluids. You can't make them take up less space unless you impose unbelievably high pressure on them. We're not going to get into that weirdness. In social science, fluid might mean something that has room for interpretation, like gender. It might describe a feeling or a mood or what someone looks like. In finance, something is fluid if it's an asset that can be converted into cash. Okay. What's a database? Well, I'm a computer scientist, so to me, the word database means things like SQL and, anything built on top of that, like Postgres, Oracle, Access, DB2, on and on and on, right? There's a million of them. But it means something very specific. But if you're a bioscientist, you might use the word database to mean a large collection of files, not necessarily, in fact, typically not, a database in the SQL or Oracle sense. It's a completely different use of that word. It took me a long time to understand that when they said database, I needed to ask that question. Which of these do you mean? And after I'd asked that question enough times, I came to understand very rarely do they use it to mean SQL or anything of the like. What's the difference between data and metadata? Now, I would say that metadata is data that describes data, right? That's how I would use the word metadata. But that's not how everybody uses the word metadata. For that matter, that's not how everybody uses the word data. This gets into a whole complicated, messy area, right? And in particular, if you design compilers or interpreters for a living, converting a human-readable high-level language into something the machine can execute, to you, code is data. And data, in the sense that everybody else is using it, is not interesting. You're interested in the code, which is your input data. Having this what is problem right now with the word repository and discussing next year's NIH data management and sharing policy. Everyone wants it to mean different stuff. Yeah, exactly. And as soon as one person wins that fight, the fight starts all over again, right? Then there's the times where data is lore. Yes, or lore is data. After all, if you are a social scientist, you may gather qualitative data instead of quantitative data, and your qualitative data could consist partially or entirely of narratives, right? Storytelling can be data, right? Yes, yeah, data and lore, the Android brothers. Not going to go too deep in that. How does scale affect how you talk about a thing? Well, let's say you're a high energy physicist, right? So you bang tiny particles together at unbelievably high speed. When you're banging two tiny particles together at unbelievably high speed, how much does gravity matter, right? On the other hand, if you're a cosmologist, so you're studying the entire universe over its entire lifetime, how much does gravity matter there? Well, for high energy physics, for tiny particles, gravity hardly matters at all because the particles are tiny, right? But for cosmology, the thing is universe sized. There's an enormous amount of mass, and it's over an enormous period of time. So if anything, gravity is probably the most important force that you study. Right? Okay, let's take a moment, and you can either put this in the Google Doc or in the chat. In fact, I would prefer, let's use the Google Doc, and I'll pull it up here. But let's go to the Google Doc and put in examples of disciplines or subdisciplines where gravity does matter, and disciplines or subdisciplines where gravity does not matter. Go ahead and add some in, right? Some of each, preferably. Gravity and matter in the same sentence is already a source of confusion. Yeah, well, and again, it depends very much who you're talking to and what you're talking about. After all, the word gravity to a physical scientist or engineer likely means the force of gravity, the attraction between masses. But on the other hand, in other contexts, gravity can mean important in a somber way, right? And in fact, matter can mean is important, right? It matters. If I recall, context switching is the term for this, changing language to suit the situation. I think that's correct, yes. And it's a complicated and messy business, right? And that's not a bad thing for two reasons. One, it makes it more interesting. And two, it gives us job security, because we in the general research business are constantly context switching. We get very practiced at it. People who are deep into a particular discipline typically do not get that much practice context switching. How does gravity bend light when photons have no mass? I am not answering physics questions. I promise that. Okay, so we're getting some really good responses here, and we'll read through some of them hopefully later on. While you all are doing that, I'm going to move on, and I've got some more things to put in the document. Science versus engineering. Science focuses on discovery. How is the world, or how is what are the general properties of a particular thing that actually exists? Engineering is focused on design. What does it take to create this new thing that doesn't exist yet, right? Which raises a question. If you've got a design project, an engineering project, is that research, right? So I had a grad student working for me. I was on his master's committee, and another person on his master's committee was a meteorologist. And when he went to his master's defense, the first question the meteorologist had was, I mean, I really like what this student has done, but how is this research? And I had to patiently explain, scientists focus on discovery, engineers focus on design. This is research about design, right? Okay. Do engineers do science research? Now, I've known some engineers who I would argue they are doing discovery. They're not doing design. They may be doing discovery in service of design, but the particulars of the research they're working on in that moment, I would consider to be, I mean, very applicable discovery, but it's discovery. What about research about software? Is that research, right? Is there such a thing as computer science research? I'm sure the computer scientists on the call have very strong opinions on this point, right? But do computer scientists even do research? This is a very uncomfortable conversation. I was once in a conversation where one of the domain STEM researchers referred to the computer scientists as IT. And I want you to imagine how that played out. There was a brief silence, followed by one of the computer scientists gently but firmly and as civilly and politely as they could muster, correcting the domain STEM scientist on the proper terminology and what IT was versus what computer science is. It was not appreciated at all. Oh, wait, computer scientists do research? I thought their job was just to help real researchers do actual research. Again, and this was the same group, by the way. I was in that conversation too, right? And, oh, that went over like a lead balloon. That did not go over well at all. No. That was followed by a tirade. That didn't land. That was a real dog. That didn't land at all. All right, how about is simulated data? So I have a lot of meteorology colleagues because OU is a big meteorology school. Depending on whether you ask us or Penn State, we're either number one or number two. Our researchers, our faculty and students and staff produce enormous amounts of data from simulations. They use simulations as their mechanism for doing forecasts or as a key mechanism. So they refer to that as data. I once used the term data to refer to the output of a simulation with a chemical engineering colleague. And he stopped me dead. And he said, oh, I can't call it data when I go to the conference. I said, why not? He said, well, I'll be laughed out of chemical engineering. I said, what are you talking about? He said, I can't call it data. I have to call it simulated data. Okay. If you're a compiler designer, I mentioned this before, then code is your data. And what other people think of as data, you don't care about. Okay, so what would be, and let's put this in the same Google Doc, so somebody please create a new header. What would be some example of disciplines that have unusual definitions of the term data? And what, in that discipline, what does the word data mean? Okay, and I missed a couple of chats here. CS is development, IT is infrastructure. Okay. Computer science is a theoretical discipline with rigorous mathematical background. It's not even programming or coding. My guess is, Chris, you like me are a computer scientist, except for organizations that have a research IT group.
No, I'm a computational and theoretical chemist, but I have read The Art of Computer Programming.
Okay. So you're not one of us, but you're on our side. Is that how you'd characterize it?
Very strong, very strong ally.
Okay, thank you. We appreciate it. All right, so while you're working on, and I see there's a lot of good stuff under the gravity versus not gravity thing. While you're working on, in the same Google Doc, working on the, which disciplines use the word data to mean what. Here's a general principle. They don't know what you know. You think they know what you know, but they don't. The most normal thing in the world is to believe that the person you're talking to already knows about the thing you're talking about. And the second most normal thing in the world is to be dead wrong about that. Most people, not surprisingly, don't know about most things. I'll tell you a story. So the guy who taught me to write grant proposals, the guy I essentially apprenticed under informally, learning how to write a grant proposal, we were writing a grant proposal together. And he was describing a thing that he was going to do computationally and describing how he would do it computationally. And he described the data structure that he was wanting to use, or sort of the structure of the thing that the data structure would represent. And I said, oh, that's a binary tree. And he said, it's a what? I said, binary tree. It's like freshman level computer science. He said, I've never heard of that. And I was flabbergasted by this. How could he possibly have never heard of a binary tree? And then it hit me. Where on earth would he have heard of a binary tree? Right? I learned about binary trees in my computer science courses. He didn't take computer science courses. He took chemical engineering courses. Where on earth would he have heard of a binary tree? Well, the answer is very simple. He wouldn't have, right? So of course he didn't know what that was. But right up until he said that, it had never occurred to me that any educated person could possibly not know what a binary tree is. It's not that I had actively thought, of course, everybody has heard of a binary tree. It just never occurred to me that that would be something that people wouldn't know what it was. That's happening all day, every day, to everyone. It's amazing. Some years ago, I met a cluster sysadmin who had only been a cluster sysadmin for a few months. And before that, they had been 100% enterprise IT. They'd spent a few months being a cluster sysadmin. And I talked with that person for, I don't know, 15 minutes. And I could tell in that 15 minutes, that sysadmin could not turn off the assumption that everybody knew everything he knew about a subject he had only been introduced to a few months before. So it was like this absolute change. He went from knowing nothing at all about HPC clusters to not just knowing something about them, and quite a bit. I mean, let's be honest, very smart person, learned very quickly, but couldn't imagine that somebody else would be in the very position he had been in just months before. And that's normal. We all do that all the time. That's the amazing thing. Okay. One more exercise. I don't know if this is the last one, but on the shared Google Doc, I want everybody to go to the shared Google Doc, and I'm going to keep going, but I want you to do one more exercise. Come up with pieces of terminology, stuff that's not in the slides, right? Where how it's used in a particular discipline or subdiscipline or sub-subdiscipline, how that term is used in that particular context is different from how it's used normally. Then give at least a sketch of how it's used in that context, and then how it's used normally, right? Don't assume that we know that term or know how you would normally think of that term, right? But give us an example, right? I already did some like data and projection. Give us some examples like that. If you have two different disciplines where it's used in two completely different ways, that's good. If you've got like how it's used in a particular discipline and how it's used colloquially in real life, that's also good. But show the different meanings. Okay. I'm going to keep going, but I want us to create a shared glossary of this kind of terminology. It's going to pay off really well. Can't open the Google Doc right now. Okay. Those of you who can get to the Google Doc, please add to it. In the meantime, I want to switch gears. I want to pivot to a completely different topic while you all are writing your terminology in the Google Doc. So please go to the Google Doc and do the terminology, okay? Enterprise IT versus research computing. Are we natural enemies or natural allies? Enterprise IT, I would distill down to the following phrase, 5 nines. That means 99.999% uptime. That's 5.25 minutes of downtime per year. Now, if you want to achieve 5 nines, 99.999% uptime, you've got to be secure, you've got to have established technology, you've got to have best practices. Everything's got to be locked down. Everything's got to be solid. Very, very, very important. Research computing is the exact upside down of that. Enterprise is 5 nines, research computing is 1.5 nines. And when I say that, I'm not making that up. That comes directly from the National Science Foundation. Okay, 1.5 nines, 95% uptime. That's 18.25 24-hour days, over 400 hours of downtime per year versus 5.25 minutes of downtime per year for enterprise. Now, when I say this to the enterprise folks, and any of you who came from an enterprise background are probably experiencing right now, your teeth are gritting and you've got chills running up and down your spine and all the blood is draining out of you at the notion of 1.5 nines. And we're going to talk about why. Okay. But in research computing, 1.5 nines, you've got to be fast and flexible, got to be able to turn on a dime. Probably not a week goes by that we don't get a request from a user for something we've never done before. That doesn't mean we have a year to figure it out. We got to deliver, right? Yeah, and exactly as Nick says, research IT doesn't always have to work because sometimes it's the first time that thing has ever been done, or at least has ever been done at your institution, right? But it's even more than that, right? Enterprise IT at my institution is all about fixing the issue, not taking or collaboration with the faculty, student, and staff. They don't take any time to think about the educational research portion. So I want to disentangle that. It's not quite that, or at least my experience. I've worked with enterprise IT folks for 20 years. They are wonderful people who have the universities and the faculties and students and staff's best interests at heart, but they work at a different scale for different purposes. So they have to address things in a different way. Right? When you've got 50,000 or 100,000 customers, you will inevitably behave differently than when you have 1,000 customers. There's no getting away from that, right? Okay. Now, when I say 95% uptime, 1.5 nines, I'm not kidding. This is straight from the NSF. They've had this exact text in 3 different solicitations for 7- and 8-figure systems, right? Frontera at the Texas Advanced Computing Center at University of Texas at Austin was the 2017 version of this $60 million machine. And I think somewhere in the $20 to $40 million worth of operations funds, in addition to the 60 million for the machine. So either high 8 or low 9 figures for that project, right? NSF expects the production resources should be unavailable as a result of scheduled and unscheduled maintenance no more than 5% of the time. By the way, they do a lot better than that. They're, I think, 98.8% or something, at least the last I looked. We also at OU were 98.8%, so roughly 2 nines, right? OUIT Enterprise is 4.5 nines. Why? Why is it that Enterprise is 5 nines and research computing is 1.5 nines? Okay. Concrete example. About 6 years ago now, Delta had a power loss in their main data center in Atlanta. They were down for 5 hours, according to Delta's own reports that they have made public. $150 million loss. That's $1 million lost for every 2 minutes of downtime. Now, you know, at my institution, if we go down for 5 hours, it's not going to be $150 million, but it will be proportional. Right? So if tomorrow is payday, we all like to get paid, right? And tonight, the payroll system crashes. Heads will roll, or assistant heads anyway, right? Enterprise IT is going to be held accountable for that failure. If you know you're going to be held accountable for that failure, you're going to do everything in your power to ensure that it fails as seldomly as humanly possible, and that when it does fail, it fails as gracefully as humanly possible. That's the only way you stay in business. Because if you can't accomplish that, you're going to be selling pencils out of a tin cup. Right? On the other hand, with research computing, again, it's the exact upside down. If we are not cutting edge, so researchers can't do new exciting kinds of research that they're promising the funding agencies they will do. It's not that we're going to get fired tomorrow, but we'll make ourselves less and less useful because we're making our institution less and less competitive for funding, right? And various other positives. So eventually we make ourselves obsolete, pointless, useless. They disband us. We're gone, right? It happens. I mentioned the Delta thing, $1 million for every 2 minutes of downtime. Let's take a look at the opposite, the research computing thing. What's the cost of downtime? Well, the first question you have to answer in order to get to the answer to that question is, who does research at academic institutions? People who are not from academia think that the answer is faculty do research. Unfortunately, that's generally not the case. Faculty do research management. Researchers, the people who are elbow deep in the research tasks, typically are students and postdocs. So especially grad students, right? Some undergrads, some postdocs, but especially grad students. On any given moment on our machine here at my institution, on any given day, we're going to have 10 to 100 people running jobs on the machine, or they've got jobs pending or whatever. And they come from 5 to 50 different research teams, right? What's a grad student cost? Well, with the sort of the highest paying grad students at my institution right now, it's around $30K of salary. Then there's some fringe, there's tuition support, there's overhead. When you add all of that up, what they call fully loaded is about $60K per grad student year, right? So if you lose a day and you've got 10 to 100 grad students, let's say 100 grad students, the top end, right, running jobs, 60K times 100 divided by 365. It's about $16,000, right? For a full 24-hour outage, $16,000, total loss to the institution. Now, slice and dice that by 5 to 50 different research teams, you're talking about $300 to $3,000 of productivity loss per research team for a full 24 hours of downtime. Now, even that is an exaggeration, right? Because researchers, grad students don't only run jobs on the supercomputer, right? They're writing papers, they're making posters, they're working on coursework. There's a million other things they have to do. So in the worst case, it's $300 to $3,000 worth of lost productivity per research team. Probably significantly less than that. Now, on the other hand, what is 5 nines cost? So I used to think the answer was to go from 1.5 nines to 5 nines, doubled your cost, doubled the cost per unit of computing and storage. Until I was in a meeting with one of the major national computing vendors. They were consulting with our IT group to help us get better. And I mentioned that, and they laughed at me. And they said, it's not a factor of 2. They didn't say the words, you idiot, but it was hanging in the air. You could hear it in their tone. It's not a factor of 2. It's a factor of 10. Okay, costs 10 times as much to go from 1.5 nines to 5 nines, right? So if I want to do that, will my budget go up by a factor of 10? No, my budget won't go up at all. I've already had this discussion with my boss. My budget is fixed. This is as much money as I get. This is what they can afford, right? So in order to get from 1.5 nines to 5 nines, I've got to cut research productivity by 90%. So I actually offered that to a physics faculty member in front of my boss one time. I said, Pat, I will give you 5 nines, 99.999% uptime, 5.25 minutes of downtime per year, in exchange for 90% of your research productivity. You take that bargain? He said, not if you live to be a million. So let the machine go down from time to time, right? Let it be junky in exchange for being able to have a lot more of it so that you can maximize research productivity per year. Because researchers, particularly faculty, are not judged on productivity per day or per hour. They're judged on productivity per year. I do one annual evaluation as a faculty member. I'm part-time faculty. I do one annual evaluation and they say, did I publish enough? Did I do, was my teaching good? Was my service good? Once a year. Is failure normal? It is so normal. So last calendar year, calendar 2021, we ran 18 million jobs on our machine. Of those, about 500,000 failed. So about 1 out of 38, 1 out of 39 jobs failed. Of the failed jobs, only about 2,800 failed due to a server failure, right? So about 2% of 1% of jobs failed due to server failure. And then there were some jobs that failed due to storage or network failure. But job failure is normal. Job failure due to hardware problems is round-off error. Right? And here's the numbers to prove it. I didn't make this up. This came right out of the S account command in Slurm. You can't have uptime without downtime. Most users don't understand that. Get users of HPC systems used to having scheduled downtime at the end of the quarter or during your recess. We actually, I think we average about 10 downtimes a year. So it's not quite once a month, but it's that neighborhood. And they're usually the better part of a business day. What are the implications for IT? Well, research computing is cheaper than enterprise, but it's also therefore less resilient. So when a researcher comes to us and they say, I need such and so, we can say, okay, can that thing tolerate 8 hours of downtime per month on average? And if the answer is no, they need to go to the enterprise side. And if the answer is yes, the research computing side is a great place to be. I actually had a meeting with a group about 1.5 years ago and asked that question. And their answer was, well, this thing can handle plenty of downtime, and that thing has to have lots of uptime. So we said, well, this thing should go to research computing and that thing should go to enterprise. And research is the test bed for enterprise. So we've got limited best practices, right? If we knew what we were doing, it wouldn't be research. But we also are early adopters of new technologies, right? We were the first kids on the block to do software-defined networking and software-defined storage and GPUs and all this good stuff, right? And then they're going to need that a few years from now. So they can watch us screw it up because we can afford to screw it up, right? They can learn from our mistakes and develop their sense of what is and are not best practices before they have to actually implement. So here's a good example. 10 years ago, we opened up our data center, very expensive, very good. The old one was from 1970. We were constantly having failures on the power and cooling systems. We sent an email to our users. We said, we're going to take the machine down for 1 to 2 weeks. In exchange, when we move it to the new building, we will stop having regular power and cooling outages. They said, it's totally worth it. And it was, we predicted very well. It was 1 week and 1 minute, 5:01 p.m. I sent the email out to everybody. You can get back on the machine. But by doing that, we proved that the power system worked. We proved the cooling worked. We proved the network worked. We proved that the pedestal flooring could handle the load, everything, right? We shook the building out so that the enterprise systems could then move in. Because the problem that the enterprise folks have is, a friend taught me a great word, all of their systems are intertwingled. Everything interoperates with everything else, right? Which means pulling any piece out and moving it to a new place is fraught with peril. You've got to disentangle and unravel. It's really tricky to do. Research computing, we literally unplugged everything, put it on a truck, dragged it 6 miles across town, pulled it out of the truck, stuck it in place, plugged everything back in. It wasn't immediate, but it took a week as opposed to months of planning. So we were the test. All right, the mindset gap. By the way, I will run out of time before I run out of content, so I'll just go until we're done. I hope, by the way, you've been putting in your definitions of data and where they're used. You've been putting in your terminology and how it's used in different contexts. And I forget what the third one is, but I hope you've been doing all of those. If you haven't contributed, please do contribute to that. You may not think you know what to contribute, but look at what others have contributed and then add to it, because we're going to need that information not so much this week, but to work on the sifted certification, the badging and such. Okay, mindset gap. So in the good old days, in the long, long ago, in the distant mists of time, and by this I mean like 15 years ago, a typical new supercomputer user came to us from a Windows or Mac OS laptop or desktop PC background. Right? And that's a pretty fair distance from Linux command line shared remote batch, which is the reality on the supercomputing side, on the HPC side, right? And for that matter, on the high throughput computing side as well. Those were the good old days. Nowadays, they're coming from here. They're coming from the phone and tablet world. They're coming from iOS and Android. So where the mental distance used to be pretty wide, now it's even wider, right? Their sense of what computing is even farther from what we want them to have their sense of computing be. Okay. Concrete examples. How do I install software on this? Well, that's pretty simple. I tap once to open the store. I tap a second time to select the app I want to install. And then I tap a third time to give the app permission to listen to my phone calls. And from then on, it's all automatic, right? It's all magic because it'll update itself automatically. Everything's beautiful, right? I don't have to do anything. Right? What about on a cluster? Well, if you're lucky, it's an easy build or SPAC, which probably the users don't know how to use and maybe don't even have the privileges to use. If you're not so lucky, then you got to do configure and make, and that can be fraught with peril, and there might be a lot of dependencies. So first you have to install a bunch of other things that you didn't know you had to install, and you discover as you're trying to make the thing that you have to install these other things first, and yada, yada, yada. That's the medium version. The worst case is it's some bizarre random thing. We had one code where it took a month to install it. I mean, not all day, every day, obviously, but it took a month of labor to get there. And the reason it took a month is because that code was hardwired to only work on one specific supercomputer. Like they hardwired locations of various files inside the code, not in a config file or an input file or something. So all of that had to get addressed. By the time our person finished deploying that code, the scientists had moved on. They no longer were using it or wanted to use it. They'd give it up, right? It's not realistic to expect all of our users. We all have users who can do this, but it's not realistic to expect most of them to do it. So we spend about half an FTE, I want to guesstimate, just deploying codes. What about storage? Well, on my handheld, if I want more storage, mine happens to have a little SDXC slot, micro SDXC slot. So I can stick in a little card that I can get for, tens or a few hundreds of dollars. I can stick that little card in there up to 2 terabytes, I think. And, within seconds, the machine will recognize it and I'm good to go, right? That's it. I go to my favorite big box store, buy an SDXC card, stick it in the slot, I'm good. If I want that on the supercomputer, I've got to write a request for proposals. I've got to work through our purchasing organization to get that out, which is a lot of back and forth. Then there's bid evaluations that come in. There's bids that come in. I have to evaluate those. We as a team evaluate those. We configure the machine we want, and then we execute the purchase. All of that is very labor intensive. The machine shows up. We have to deploy it. That's very labor intensive. Then over time, we have to maintain it. Maybe we're expanding it, and eventually we decommission it, right? So just getting to the point of deployment, anywhere from 3 to 12 months, depending on the particulars, right? Getting through the lifetime, 5 years. What does storage cost? On your handheld, tens to hundreds of dollars, which gets you tens to hundreds of gigabytes. On your laptop, tens to hundreds of dollars, that's going to get you terabytes of spinning or gigabytes, terabytes of SSD, significantly less, right? At large scale, a single copy, 1 petabyte usable on tape is about $6,000. On spinning disk is about 47 grand. That's about 8 times as much as tape. on SSD is about 330 grand. That's 56 times as expensive as tape. And by the way, at our scale, petabytes is normal, right? How many of you, your research computing organization has petabytes of storage? Either put it in the chat or do the hand raising thing in Zoom. How many of you that's normal, petabytes? I've got 1, 2, 3. Okay, so we're running, it looks like about 15 to 1 on normal versus not normal, right? Petabytes is normal. Is petabytes normal on a handheld? Is petabytes normal on a laptop? No, of course not. But on a large scale system, it's normal. Why else is research computing hard? Research computing is hard for a number of reasons. The mindset gap we've talked about. And by the way, their tolerance for how long it takes to get them productive has not changed. Everything else has changed, but not their tolerance for how long it takes to get them productive. That has remained 1 hour. If it takes longer than an hour, they give up. And they don't just give up on it, they give up on you. Okay. Research computing systems are getting harder and harder to use. Always, always harder to use. For example, the storage hierarchy keeps getting deeper. In the long, long ago, we had registers and RAM and probably tape, right? Now we have registers and cache and RAM, but we may have that non-volatile memory. So Intel calls it Optane, for example. We may have flash. We could, in fact, have multiple layers of flash, but let's not even dig into that. Then spinning and then tape, right? We've got all of those layers, and they're adding more all the time. Right? And parallelism got more hybrid. In the olden days, we had MPI and OpenMP. Now we have CUDA or various other, I mean, the accelerators have made this stuff really weird, right? And then the third dimension of this is more researchers need research computing, and that's in 2 dimensions of its own. One is more disciplines. So in the olden days, it was almost entirely physical sciences and engineering. Then we added between 10 and 20 years ago, we added life sciences. They started to be big consumers. Now we've got social sciences, we've got humanities, we've got arts, we've got business. It's a much bigger group than it used to be, a much bigger collection of disciplines. And within every discipline, more and more researchers needed as well. Okay. I'm low on time, so I think I'm only going to get through this part of it. And I'm going to kind of zip through this a little bit because Bruce is going to go into much more detail this afternoon about this topic. But why are researchers the way they are? And we're going to break it down by different types of researchers. But let's start with, what are faculty rewarded for? At research-intensive institutions, faculty are basically rewarded for 3 things: bringing in money, publishing papers, and graduating students. At teaching-intensive institutions, there's less emphasis on bringing in money, and there's less emphasis on publishing papers. Less, not none. And more emphasis, therefore, on graduating students. Graduating includes teaching, mentoring, all of that stuff, right? Getting them through the process. Faculty are not rewarded for having good computing. Here's the thing. If you are not rewarded for something, then you are implicitly punished for it, in the following sense, that if you had taken that energy and time, and in some cases funding, and devoted it to the things you are rewarded for, you would have got more reward. Because you devoted that to good computing, you get less reward, which is an implicit punishment, right? So researchers obviously don't want to pay any more than the absolute minimum for their computing. They'd prefer that that be 0. At most institutions, it's not 0. Also, their mental model for what storage and computing cost is what it costs at their local big box store, right? What does a tablet cost? What does a laptop cost? What does an SDXC card cost, right? Or maybe a USB drive. What does that cost? By the way, I can answer that question. A USB drive is somewhere around $20, $25 per usable terabyte. I don't know anybody who can provide that at large scale for that cost, right? Not reliably. Now, suppose you're on tenure track, but you're not yet tenured, right? Your job, your goal is to get tenure, right? You don't want to get fired because your choices are you get tenure, you get kicked out as a general rule. I know of a few exceptions, but to first order, that's true, right? So if I'm on tenure track, I've got to publish a lot of papers, got to bring a lot of grant money, I got to graduate a lot of students. And if I don't do that, I'm fired, quite literally, right? So I need everything to work now and all the time, right? I can't wait. Don't tell me it's going to be a year from now. If it's going to be a year from now, I'm already gone, right? I can't wait. Why? Well, the tenure process is 7 years, right? Except that year 7 is the year where if you didn't get tenure, you're looking for a new position. Okay. So it's 6 years. Well, except that year 6 is the year you're being evaluated, which means you have to turn in your tenure package at the beginning of year 6, which really means it's 5 years. Except it takes about 6 months from the time you start writing a journal article to the time it actually appears in print, sometimes longer. Right? So sometimes it's 6 months from when you submit it to when it appears, or even when you're told it's going to appear, right? So really, you got about 4.5 years to do everything you're going to do to be judged on the question of, should this person get a job for life? Now, I realize it's not literally that, but I'm simplifying to make this point. 4.5 years is not a lot of time. Your tolerance is 0. Now, on the other hand, if you've already got tenure, then you should be fine, right? You don't need to worry about this stuff. Well, you've already developed the mental habits. Those are awfully hard to break. And getting tenure is not the final reward of your career. You want to get a raise. You want to be promoted from associate professor to full professor. You want to get a named chair. You want to be elected to the appropriate national academy, whatever it may be. You still want those rewards, and they're still based on bringing in money, publishing papers, and graduating students, right? So you still think, I need everything to work now and keep working reliably, right? What if you're research faculty? So you're not even on tenure track. If I don't bring in grant money, I'm laid off, right? If I only bring 6 months of grant money to pay my salary this year, well, they'll let me work part-time, but they're not going to pay the other half, right? And I got to keep publishing because that's the only way to get grant money. And also, I don't want to be on soft money forever. By the way, I've been on soft money. Being on soft money sucks, right? Hard money, internal budget is way better than soft money, right? So I need a track record of graduating students because I want to get a tenure track job somewhere, right? Now, what if I'm a postdoc? Well, I got to publish a lot. Otherwise, my postdoc advisor will fire me, right? And by the way, in some disciplines, people typically do multiple postdocs in a row before they get a permanent position, right? So I need to learn how to get grant money and ideally get a track record of getting grant money so that I can get that permanent or at least future position, right? Make myself attractive. If I'm a student, my job is to graduate. Well, anything that delays graduation is costing me money, both in the direct literal sense of I have to pay tuition or whatever it might be, and in the sense of foregone income that I didn't get because I hadn't graduated yet, so I didn't take the job yet. I calculated that the dollar cost of getting my PhD was between $250,000 and $500,000, just based on what I would have got paid coming out of my undergraduate degree, what they were paying at the time, and then taking into account how things changed and how my skills would improve and so on. Between $250,000 and $500,000 gone, never to be seen again. Now, I'm having a grand time, so it's worth it. But every year you spend is a year you're not earning. Let's talk a little bit about research funding. The academic funding model is this: a random amount of money shows up on a random date and is available for a random duration, right? Typically that's a grant, could be a contract or a cooperative agreement or something like that, but these are all more or less the same thing, right? And when I say it shows up on a random date, I'm not kidding about that. So I was on a grant one time where we were told in, I think it was late June, that the grant was starting in early May. That was the official start date of the grant. And the money didn't bank until I think July. But the project had already begun even before we were told about it. Right? It's random, right? You say what you want, but that doesn't mean you get it. Grants typically favor spending as much money as possible on researcher costs, so salary, fringe, indirect. They disfavor equipment, and they strongly disfavor services and non-researchers, right? And there's not a lot of credit for equipment, services, and non-researchers. So faculty don't want to put their budgets into that, right? If there are recurring charges, that's really hard, right? You drop a data set into a metered system where you have to pay a recurring payment every month. You got a 3-year grant. Well, in month 37, they will be happy to delete that data set for you because you can't pay. And the likelihood that you're going to be able to pay for the storage for that grant's data on the next grant is not great, because the next grant might be on some completely unrelated topic, right? Some academic institutions, particularly the high-ranked ones, have some internal funding for their researchers. I had a conversation once with a colleague at one of the Ivy League schools. And because of the conversation we were having, I went and looked up the number of faculty at each of our institutions and the number of dollars, research dollars at each of our institutions. And it turned out that his institution 4 times as much external research funding as at my institution. And at his institution, the amount of internal funding, university funding per faculty member for research was equal to my institution's amount of external funding. Our internal funding is not literally 0, but it's awfully close as a percentage of the total funding. So at his institution, you know, if you had a bad patch, you would be carried through it. It's not a crisis. At my institution, if you have a bad patch, there's no money, right? And my institution is relatively high ranked as these things go. The problem with the top 50 is there's only 50 of them. Getting grant money is hard. It's the law of large numbers, right? On average, you have to submit 4 grant proposals to get 1 funded, right? Which, by the way, we proved with the sifted grant because we had to submit 4 of them and finally got the 4th one funded. That was a little bit too on the nose, but that general pattern is true. You can see it varies by discipline area, to be sure. It also varies by state, but basically, if you're not constantly writing grant proposals, you're not funded, right? That's why I say faculty don't do research, they do research management. They write proposals, they manage their students and postdocs and staff if they have them. They help with the writing of the papers, but they're not typically the one doing the bulk of the writing. They're doing research management much more than they're doing research. That's why they so jealously guard their sabbatical time, because that's one of the only opportunities they have to actually do research, right? Get their hands a little bit dirty. And when you talk to faculty who've just come back from a sabbatical, they're so excited because they just spent an entire semester actually doing research, and it was like the best thing ever. They had forgotten how much they liked doing research, right? So how is research computing funded? Well, we talked about grants, right? But there are a lot of other methods as well. And particularly research computing often has a broader set of funding opportunities than research, right? At academic institutions, it's some or all of the following. There might be a regular annual budget for research computing. Often that's true of personnel, for example. At some institutions, including at mine, it's also true of some of the hardware. There can be internal funds at a random time, like somebody can say, oh, you know what, we need a new supercomputer, here's 7 figures, right? And then you hope that 4 or 5 years from now, you get another chunk of money. Grant funds at random times, right? So we just got a grant for some GPU cards through the NSF's Campus Cyber Infrastructure Program. At public institutions, in some states, there can be a state appropriation. That's usually fairly random, but even if it is non-random, the state legislature giveth and the state legislature taketh away. I will give a concrete example. I won't name the state. But there was a state about 10 years ago, they had a governor who was very excited about this and who devoted 8 figures for research computing at a large number of institutions across the state. And then a new governor came in, done. It was over, right? I think that's probably the most common. In another state, the governor got 8 figures and gave it to a group of people to buy a big machine and run it. And they had a model for how they were going to make this work and how to make it sustainable. The model turned out not to actually work in practice. They ended up selling it off for parts. Usage charges, that's not very common. I actually did a survey of OU's aspirational peers and found that only a very small number of them do cycle charges. There's condominium purchases. Those are very common, where researchers are buying like more compute servers to add to the cluster supercomputer. That's quite common. Most institutions that have a cluster supercomputer have that option. Not all, but most. But usage charges is quite uncommon. And there's a mix, right? And then some institutions are perfectly happy leasing. So you can have budget on a regular cadence, but buying a machine once every so often. And some institutions don't like doing that. In some cases, some in other cases. My institution used to do leasing, now does buying only. Doesn't do leasing anymore. How should faculty spend their grant proposal writing time? Some institutions, you have to write a proposal to get time on the machine, the internal machine to the institution. And of course, at the national centers, that's true, right? You've got to write proposals to get time. We don't do that at my institution. The reason is very simple. Researchers, and particularly faculty, have a limited number of hours per year they can devote to writing proposals. We would like that they devote that time to getting external funding. That means we don't want them to spend that limited number of hours writing proposals for machines that we've already funded. We want them to bring in external money, right? Will the funding model change for cloud computing? I haven't seen any evidence that it will. So far, I haven't seen evidence of the internal model changing to support cloud computing. I only know one institution that only does cloud computing and does not have on-campus resources. The difficulty that I've seen with metered cloud, other than that, month 37 problem, the difficulty that I've seen is when you have effectively unlimited resources, it's very hard not to consume unlimited resources and therefore to run up unlimited consumption and unlimited costs. So let's say you tell your grad students, okay, folks, we have $2,000 a month that we can spend on research computing in the cloud. And they will go do research computing and they will come back to you after 2 weeks and say, hey, we spent our $2,000, but we have a paper due next week. Can we have more? Well, you're going to cave every time, right? Eventually, you're going to have to start laying off your researchers because you don't have money, right? Whereas if there's a natural limit to how much capacity there is, you never have to do that. You do have to be careful and deliberate in your planning for doing your runs, but you never have to lay anybody off because you're spending all of your money on buying time on somebody else's machine. Coming from 2 former institutions that moved to consumption models, I think it's going to become more common. Sorry, I'm losing the thing here. Hang on. If you intend to have hardware that's close to what the researchers are hearing about, we'll probably have to dig deeper into that. We are pushing hard for our system to become the cloud resource in and of itself for our researchers. You mean like an internal cloud, Lily? Is that what you're referring to? Yeah, okay. Yeah, and we have that here. We use that differently from how we use our HPC resource, but same kind of idea. I know I'm running out of time. There is time in the beginning of the lunch period for us to do some questions, so I'll just try and wrap this up. here's some things you can say to a researcher that will make things better. Doing it this way is cheaper than how you're currently doing it. Oh, they love that, right? Now, they're not interested in cheaper for the institution. They're interested in cheaper for their own budget. They're somewhat interested in cheaper for the institution, but they're definitely interested in cheaper for their own budget. Or equivalent, for the same number of dollars, here's how it would be so much better. Here's how you can get a lot more bang for the same number of bucks, right? Those are roughly morally equivalent. Keeping control of it. You get to decide how to use your piece. So our condominium model is, if you buy a server, we'll maintain it at no charge, but you get to decide who's on it when, right? You can share it with whoever you want. So if you want your collaborators to use it, you can have your collaborators use it. We will take care of it for you. Your students won't have to maintain it for you, right? They can devote their time to doing their research. Okay. And real quick, how do you find researchers? Well, the answer is you go to your institution's website, click on academics, pretty much everybody's got that link, search for the departmental websites, and then start looking through the list of faculty, and maybe if there are postdocs listed or whatever, and just look at their research descriptions. Most institutions, they provide a description of their research, at least research-intensive institutions tend to. So read those research descriptions and look for keywords. Computational, numerical, that's especially popular in engineering contexts. Parallel, especially you see that in CS. Informatics. Omics can be a little bit of a clue, but that's less guaranteed. In chemistry, you do now see computational chemistry as listed as an area of chemistry. Historically, they were more likely to list themselves as physical chemists. For a long time, computational chemistry, it appears to me at least, was sort of looked down on, whereas physical chemistry was seen as normal and legit. So look for those folks. And these are just some examples. There's plenty of others. You develop a feel over time, right? Yeah, I agree that for non-STEM, this is not always a good way to approach it. It's also true that there are a lot of disciplines where they don't talk about the computing as core to the research discipline. So you may have someone engaged in digital humanities, but they don't couch it in those terms, right? Yeah. But once you've identified some people, then you contact them, right? Send them an email, right? Faculty get cold emails all the time. This won't bother them. Tell them who you are, what you're up to. If you're writing a proposal, oh, they love it when you're writing a proposal. If you're writing a proposal, tell them what the program is, when it's due, and how much cash you're going for, because they're very interested in that. And ask them what their needs are, right? Go to faculty meet and greets, right? Most institutions have these, like new faculty have like a seminar series that they go to, right? Once a month or whatever. In the olden days, and now it's starting again to be in person where you get a free lunch. They love it if you show up, right? You can usually ask the organizer, hey, can I get 5 minutes to do my elevator pitch, right? Or half an hour if they want, right? Visit them, right? Go to their office. Even better, take them to lunch. Oh, people love it when you take them to lunch. There's very few people who will turn down a free lunch. Very, very few, right? And ask them questions, right? Ask them what the research is about. What are the computing and data intensive aspects of it? And this is one of my favorites. This is the aspirational question. Suppose I could give you an infinitely large, infinitely fast supercomputer. What research would you do if you had that you can't do right now? Oh, they love that question. And it really, because they usually don't think in those terms. They usually think in terms of what can I do with the resources I have access to, right? And that constrains their vision. Now, I tell them, I can't get you that, but we can get you closer and closer. Okay. So I hope you've been doing the terminology in various disciplines. If you're not, please start doing that. We really want to get that into the document because that's going to be very useful for all of us. If you can get us some of that today, that would be ideal. Whoops. Okay. Wow, and my timing is perfect. It's exactly noon. I am happy to stay and answer questions. So you're welcome to put questions in the chat, and I know some of them have already shown up. How do we recruit new CI facilitators? You have asked an excellent question, right? And it's not necessarily trivial to do. What we do is we put out a description of what the work is like, and we make sure we describe it in a way that it sounds fun and interesting. They are out there, the people who would be interested in doing this. Some of you are here. Many of you are here. 173, well, 172, I'm here too. I chose this years ago. But they're out there. You just have to be able to describe what it is that the job entails in a way that makes it exciting and attractive.
Henry, that comment was in context of taking the students out of doing the administrative work.
Oh, and getting them to be facilitators?
Yes. So if we do that, how will people find out they want to be facilitators?
Right. And it's always been a big challenge. My experience with HPC in general, this is not constrained to researcher facing. When you show it to people, they think well, not everybody, but a lot of people think it's really exciting. And then they want to get involved and they ask you the question, how do I get involved? Mm-hmm. Right. We had an undergrad years ago who came on a tour, just saw the machine, and his eyes got as big as saucers. And so he wanted to know what he could do to get involved. And I said, well, why don't you just start coming to our help sessions? So he started showing up at the help sessions. And after a while, he started answering questions, because just sitting in on the help sessions started to get him the feel for what was going on. We hired him as an intern. That is, we shifted him from the enterprise side into our group. And then when he finished his degree, we hired him full time.
By the same token, when I was at Penn State, we recruited graduate students to work the help desk and to basically work as facilitators while we were doing a large scale project of migrating from one system to another system. And I think that was a great way to get some really top-notch people who were coming from, who were probably going to end up being research facilitators.
Right.
So.
Sorry, and there's been some discussion in here in the chat, and I want to try and catch up. Doesn't work in digital humanities and arts. Yeah, I think we talked about that a little bit. Looking for machine learning helps, sure. And basically, hang on, sorry, I'm jumping around in the chat, making it a little bit tricky. How I got in the field, but that was via computational biology. If you market things to the PI as saving the grad students the work, that takes away some of the exposure that brought us in. Right. So if the grad students who are doing the domain STEM research or non-STEM research are not being put to work as part of the research computing team, and at scale, they can't be, right? There's no money for that. And many institutions, and mine, as far as I'm aware, is one of them, we're not allowed to use volunteers for positions that could be filled by paid professionals. So in that context, what you have to do is give them exposure to research computing as research computing, in addition to the specifics of their internal to the discipline research. So one of the things we do is we do supercomputing tours. But in addition to that, of course, we're doing these help sessions. And there's an instance where the researcher is being exposed to facilitation. And so if this is something that they find attractive, then they can come to us and say, how can I get more involved? And we have that happen from time to time. In my experience, most researchers don't ask that question, but there's a subset of them that realize that they like the figuring out how to help even more than they like the doing their research. That was certainly true in my case. I am not in love with doing research. I'm absolutely in love with helping researchers use computing to do their research better. More questions? Anybody else? I'll give you a virtual dollar.
Yeah, I've got a question.
Okay.
So I have just been, I recently got into the HPC world, and I'm basically just learning how to be the system administrator for our supercomputer Duke. So I haven't really had the opportunity to be a part of research. So my curiosity is with, like, when you use the phrase, you love helping researchers figure out how to make supercomputing like work for their research. Is that a skill that you develop over time? Like, how do you know what things would be helpful to be researched at the scale that a supercomputer can do?
Right. And I agree with exactly what you said. It is something that you learn from experience. And for people who have not done research themselves, that often means that they come from some other area of computing. Enterprise IT is common, but by no means the only place they may come from. That often means they bring some sense of the notion of scale. The distinction between laptop scale versus large scale. And that's really the first entry point, is a researcher who has a problem that's too big to fit on a PC, right? When you encounter an issue like that, the question becomes, how do you port that problem from their PC, which typically is not a Linux PC, right? How do you port that problem to the research computing environment? And that first step, just moving it from the PC to the research computing system, that first step is primarily technological, right? Now, it happens that it drags along with it in its wake a human problem, which is helping the person think in terms different from laptop scale, right? And you can't say that that's what you're doing, because then they run screaming into the night. So you have to get that information to them without making it obvious that that's what you're doing. This is, I think, the nature of teaching. A lot of teaching, at least the way I do it, a lot of teaching is providing someone with information that they don't yet know they need without telling them why they need it. Because if you tell them why they need it, that's frightening. Whereas if you just give them the information, they accept it. So that people skill of knowing what to say and what to avoid talking about until they're already drawn in, knowing the order in which to talk about things, that's something that you develop over time, right? And I think that's a great question. And there are no simple answers to a question like that. I think to the extent that you can distill it down, it's do it for a while, and especially do it with other people who already are experienced at it. And ask them why they do things. So one of my favorite kinds of questions are questions of the form, why did you? Right? And I love it when people ask me those questions, because then I get to be, you know, a know-it-all show-off, right? I love explaining, I chose the following order, or I chose to highlight this and to de-emphasize that because. And you'll find that a lot of people enjoy explaining these things. They enjoy talking about what they've discovered. It's the same as with researchers, right? You may have noticed researchers love talking about their research, and they have a heck of a time finding anybody outside of their research discipline who can be bothered to listen to them. Well, the same is true of us, right? So if you get someone in a mentor relationship and you ask them questions, how did you know that you should do this and not that? Why did you do it in that order? Not everybody wants to answer those questions, but for a lot of us, well, nobody ever asks those questions. And we worked really hard to figure that out. So we love having an opportunity to talk about it. Did that help?
Yeah, that was great. Thank you so much.
You bet. It's hard to convert people from Windows to Linux. It is. In the context of research computing, Linux is like democracy in old age. It sucks except compared to the alternative, right? What would you want most, Henry? What would make you most happy, productive, etc.? Ooh. What a great question. I'm going to try and avoid questions like a bigger budget or answers like a bigger budget. Because I feel like that's not helpful. I would like to have more time in the day to develop relationships with our researchers and spend less of my time doing what I've come to think of as retail, like helping people buy condominium stuff. I've done enough of the latter that it's no longer emotionally rewarding, and it is very time consuming. Okay. New good tools and systems in HPC are developed and introduced over time. It's an organized opportunity to learn that for research. In the research computing world, I'm going to say there are no organized opportunities. The best you can hope for is disorganized. There's the famous, that was his name, the guy from Oklahoma, the humorist, Will Rogers, this famous Will Rogers thing. I don't belong to an organized political party. I'm a Democrat, right? It's the same principle. I don't belong to an organized profession. I'm a research computing person, right? There are opportunities. They are not as well advertised as they ought to be because advertising to our community is tricky. We've started providing normal courses which use comforting web-based interfaces running on the research computing hardware. So I assume you're referring to stuff like Open on Demand. And that's been, I think, a big win for our community. Just having a web interface in front of the machine, I think, is really valuable in making use of the machine somewhat more palatable. In our case, the info security guys helpfully removed all the, I having difficulty seeing this, something stuff. Oh, SSH stuff from their Windows machines. Yeah. You have to develop a good relationship with your enterprise IT colleagues, especially information security and networking. Again, if they don't believe in you, they won't believe you. So you have to get them to the point where they believe in you. And that takes time and it takes relationship building. I flatter myself that we've done a pretty good job of that here. We've worked very closely with our IT colleagues, our enterprise IT colleagues, to make sure that they understand the value of the work we do, why we do it in the way we do it, and what benefit it provides to both the university and to central IT as an organization. Can the capabilities of HPC depend on command line scripts be set to be user-friendly once devised? So I'm going to give you two answers to that question. Yes and no. So Open on Demand is a great resource for going in that direction. There's limits to what it can do. But on the other hand, creating an environment for each of the thousands of applications that researchers use. Like we support in excess of 600 applications at my institution. The national centers typically support several thousand. Creating for each one of them its own user-friendly interface, the cost of doing that is laughably out of bounds. So if I mush all of that together, the answer is up to a point, kinda. In fairness, some of the models we domain science use are programmed in Windows-specific languages and libraries and require Windows to run. Yeah, absolutely, that's true. And porting them to non-Windows environments, either you can't do it or you can do it, but it's very labor intensive, or the better solution is to run Windows as a guest OS inside like a cloud resource or a container system, well, cloud resource really, some kind of virtualization system. Let's let's see, we're planning a Windows-based cluster here to provide more stubborn users or software that doesn't work on Linux. Yeah, so we have our internal research cloud, and we provide Windows as a guest OS, just not as the host OS. Students become naturally trained to operate in a Linux environment and later become researchers. This new wave has to be user-friendly, commands, documentation, step away from serial number one. I would love to believe in user-friendly, but I've operated in a user-hostile business my entire career, which is research computing. And if it hasn't changed in the last 30 years, I don't think it's going to change in the next 10 years. I could be wrong, but history is at least a reasonable guide. You know, they say history doesn't repeat, but it does rhyme. Web-based submission system with or without Samba can also do wonders for the Windows folks. Jupyter Hub, Galaxy, Open on Demand. SPAC-IO certification be a good idea. For system administrators, I would think so. Or at least it wouldn't be a bad idea. I honestly, off the top of my head, I'm not sure I've met anyone who at least has told me that they have a SPAC certification. Common mistake that people make when trying to design something completely foolproof is to underestimate, I feel like I know where this is going, the ingenuity of complete fools. Yes. There's also evolutionary pressure on idiot proofing to produce more clever fools. Windows subsystem for Linux and Windows terminal is a nice entry point to introduce Linux command line to people. Did I get all of the, I think I got all of it. Okay, yeah. Yeah, no, I'm quite serious when I say user hostile. We are an enterprise government IT acquiring an agency supercomputing environment. This is all going to be very new to us in a different paradigm. First question my supervisor asked was, what was the disaster and recovery environment? So that is a great question, in fact. And at my institution, the answer is we have a tape archive and the secondary copies go to a different campus of our institution. Now, we live in a part of the country where 24 miles is sufficient because the kinds of natural disasters we get around here are not large in area. We don't have hurricanes in Oklahoma. If I lived in a hurricane-prone area or something like that, then I would want my disaster recovery to have a much greater geographic distance. Beyond that, the researchers have to decide what data to retain, because that is something that they construct their own agreements with their research funding agency about what needs to be retained, what needs to be shared, what should be private, et cetera, et cetera. That's on a not just a researcher by researcher basis, but on a project by project basis. So we provide the capability to live up to those agreements, but we do not impose a set of rules on those researchers, because we would be overly restrictive to half of them and underly restrictive to the other half. In my experience, if you really explain things carefully with patience, most users are willing to learn the command line. More often than not, they're just understandably overwhelmed, and we'll get into, sorry, the command line if you guide them well. They'll also feel really grateful that you taught them something they'd never thought they'd learn. Yeah, and in fact, in addition to providing software carpentry workshops here, and I think a lot of academic institutions do that, and some non-academic as well, we also have some written exercises, some Word docs that go with, a directory on our cluster that people can copy, where they can do some exercises to learn the basic Linux commands and to learn the basic batch commands, so that they can go from no Linux experience to productive. I don't want to say quite in an hour, but in not very long. They can get through that process in, at worst, a few hours. And they know enough that they can be productive. They don't have to know very much. They just need to know a little. And it's a guided exercise where all the steps are written down in excruciating detail. But on top of that, we're there while they're doing it, so they can ask questions when they inevitably get stuck. And there are always people who get stuck. They missed a space or a period or whatever, and they didn't read the error message or didn't realize it was an error message or whatever it might be, and they need to backtrack and so on and so forth, and they need someone with more experience to help. Yeah, absolutely. Good. Well, I know I'm eating into your lunch hour for many of you, so why don't we go ahead and wrap up? And at a little over an hour from now, Bruce Mason will be presenting about faculty, tenure and promotion and all that good stuff, incentives. And especially if you are not faculty yourself, getting exposure to those ideas is going to be immensely helpful to you. This is absolutely core to being successful as a research computing facilitator at an academic institution. Now, if you're not at an academic institution, of course, the structures are a bit different, but it's valuable to understand faculty in order to be able to work effectively with researchers in an academic institution. So I look forward to seeing all of you in a little more than an hour. Do go back to the Google Doc and put in more answers, more responses. The more information we share, the better all of us will be for it. I'm going to go ahead and stop the recording. If I can find that. Stop.